We're going to introduce two tools in logic, which are the universal quantifier and the existential quantifier. So far, maybe you've been working with propositions, which are statements that are either true or false. So something like 2 is even, or John passed the test. These are propositions because we can assign truth values to them. So 2 is even is true and John passed the test. Well, let's say it's false. However, sometimes we want to say things like every student in the class passed the test, or there exists a number that is both even and prime. Well, these are not simple propositions. They are statements about a whole set of objects, like all students or all numbers. That's where quantifiers come in. But to understand quantifiers, let's first take a look at predicates. A predicate is a sentence with a variable in it. For example, x is greater than 3. This is not a proposition because we do not know what x is. But once we give x a value, like x equals 7, then this becomes 7 is greater than 3. And then we have a proposition because now we can assign a truth value. We know that this is true. We usually write predicates like this one as something like p of x, where p is a predicate and x is the variable. Okay, now let's get back to quantifiers. First, the universal quantifier. This one lets us say that something is true for every object in a domain. We write it as for all x, p of x. So remember, p of x is our predicate. And we are saying that this holds true for all x. So for every object in the domain. For example, we could say something like all integers are less than their square. We can write this as for all x in the set of integer numbers, x is less than x squared. So we are specifying the domain we are dealing with here, which is the set of integer numbers. We have our predicate, which is x less than x squared, and we are saying that this predicate is true for all x in our domain. But this isn't actually true, is it? This is actually false. Why? Because, for example, when x equals 0, or when x equals 1, which, by the way, are both elements of our domain, x is not less than x squared. So our predicate does not hold true, which makes the whole statement false. That's very important. For a universal statement to be true, it must hold for every value in the domain. That's what the for all means. So just one counterexample like the ones we've given here makes the whole statement false. Now, the existential quantifier is used when some object in the domain satisfies the predicate. We write it as there exists x such that p of x. Again, p of x is our predicate, and we are saying that there exists at least one x which satisfies this predicate. For example, there exists an even prime number. This is true. Why? Because we can find at least one number that is even and is also prime. And that's enough. We don't have to go any further. Because again, when we're saying that there exists x, we're saying that there exists at least one x. If you can find at least one, then this is true. So we can write there exists x in the set of natural numbers such that x is even and x is prime. By the way, we're talking about the number 2 here. So again, for an existential statement to be true, we only need one value that makes it true. Let's see a famous example where quantifiers help express a deep mathematical idea. The mathematician Euler once conjectured that the equation a to the fourth plus b to the fourth plus c to the fourth equals d to the fourth has no solution in positive integers. This means that there are no positive integers a, b, c, and d that satisfy this equation. In logical notation, we can write this as for all a, b, c, and d in the set of positive integers, a to the fourth plus b to the fourth plus c to the fourth is different than d to the fourth. This is a universal statement, so it claims that the equation is false for all choices of positive integers. It took over 200 years to prove Euler wrong. In 1987, Noah Melkis found a counterexample. That means this universal statement is actually false. So we can also express this as an existential truth. We can say that there exists a, b, c, and d in positive integers such that a to the fourth plus b to the fourth plus c to the fourth equals d to the fourth. This is logically the negation of the universal claim. And that brings us to an important rule. The negation of a universal statement is an existential one, and the opposite is also true. So we can say that not for all x, p of x is logically equivalent to there exists x such that not p of x. And also not there exists x such that p of x is logically equivalent to for all x, not p of x. Understanding how to switch between these two is a very powerful tool in logic.